Okay, thank you everyone for coming. I'm going to be talking about a research prototype that we've done in the Semantic Research Labs. Basically, this is trying to address the problem of too many agents being installed in every virtual machine. So this is not kind of an offensive technology. This is meant to be a security solution. So I'm going to basically talk about this prototype, how it's implemented. I'll just briefly touch on the performance, just in kind of a general way, and then maybe consider a little bit where we could go from here. Okay. So the real goal of this project is to mainly focus on the enterprise environment, because in general, if you're going to have something like a hypervisor with a large number of virtual machines, you're usually talking an enterprise environment. Although there's things like VMware Workstation or Virtual PC, this isn't really used too much to run multiple VM instances. So this is mainly focused on kind of an enterprise environment where you would have important applications inside virtual machines that you want to protect. Okay, so let me just mention kind of what a typical enterprise environment would look like. I mean, granted, this is very simplified, but I'm just going to kind of use this as a matter of illustration. And I've also tried to use kind of OS agnostic terms here. I mean, this could be a Windows enterprise domain, or these could be Linux VMs. In that sense, it doesn't really matter too much what the OS of the virtual machines are. So in general, when we're talking about a workstation in a typical environment, this could mean a physical machine that's sitting at the desk of each employee. And the agents mean the software which is permanently running inside of the workstation. These would be things like, in Symantec's case, Live Update, Semantic Antivirus, things like this. It might also be Altiris. So there's these general agents which are kind of permanently inside the workstation, and they do various tasks like keep the computer up to date, or keep the virus definitions up to date, or check for viruses. When I say domain, I basically mean all of the enterprise together. And here a domain server would mean something like the central location where you keep track of user credentials, where you push new software updates from, and things like that. And the domain administrator just means the person who is responsible to keep all of the workstations up to date. Or in general, the domain administrator is responsible to manage all of these workstations. So now, what's wrong with this model? So in general, I've broken this into kind of three categories of things that make this difficult. If you're talking about a company that has 10,000 or 20,000 employees, it becomes a big effort to manage all of these workstations. Okay, so the first general problem is just the administrative headache this entails. So, for example, if you have 10,000 workstations, one effort is just simply trying to keep all of the software on all the workstations up to date. For example, if some machine has some problem during the installation or during an update, what can you do? You might need to manually go to the machine and see what broke, see what's going wrong. Another problem with this is that there's so many pieces of software that you need in a typical workstation, like the update, the antivirus, maybe a host IPS. There's a lot of different technologies which are needed. Now, this requires a lot of effort to keep all of this software on every workstation and keep them all running smoothly. And now I'll mention more about this under the kind of the security problem. But now just consider if you have some antivirus which somehow gets disabled. So what can we do now if this machine becomes infected somehow? We might need to physically take control of this machine to to clean it up. Now, another problem is just the wasted resources. So, consider a case where, in a typical enterprise environment, most of the employee workstations probably have the same agents, they have the same software, they do the same general tasks. Now, there are obviously some variations, but I'm just talking in a kind of a general form. So, in this case, now let's imagine all of these machines are running Windows. So, perhaps 95% of all of the files on all of the workstations are the same. They all have the same kernel32.dll, int.dll. A lot of the files are going to be the same across all of them. Now, it might be true that we only scan the file once for a given workstation, but that file might exist across all of these different workstations. So we're at least one time per workstation going to be scanning these files. So, here it's kind of the problem that we've got a lot of different workstations and they all have to do some of the same tasks, but we don't have any good way to kind of coordinate between these different workstations. So in general, we need to do some redundant activities across all of the workstations. And now, given we're talking at a security conference here, obviously the security aspect is kind of one of the more important ones here. So the obvious problem that we have here is that you've got your security software and the thing you're trying to protect running in the same context. So, you've got, for example, a rootkit which is running at ring 0, and you've got some kernel driver meant to stop or protect against rootkits running at ring 0. So it's really just a question of, if the detection software detects the threat before it has a chance to do something, then the security software wins. And if the rootkit or the virus is undetected, then it wins and it has a chance to disable the antivirus software or the security software. So in general, there's an obvious problem here with having security software and the threat potentially having the same privilege level. So now, if a machine were actually compromised, so if, for example, the signatures are out of date, let's say, and so at the time that the virus got onto the system, the signatures were too old. Now you update the signatures, but maybe now it's already too late because the virus has already implanted itself. Maybe it's modified some important binaries. There's not a lot that you could do if your whole OS has been compromised. Really, the only thing you could do is, let's say, get a rescue CD and boot off the rescue CD. But now this obviously requires you to gain physical access to the machine. So if you're in a workstation environment with 10,000 computers and let's say 1% of them occasionally get infected, this is a lot of time spent going to visit these machines and physically repairing them. So obviously this is going to take a lot of effort. So what this project is mainly about is, can we eliminate the need for all of these agents inside all of these virtual machines? So if we can find a way to achieve the same tasks but do it in a more coordinated way, or avoid to doing the same activity across all of the workstations, then we can obviously solve a lot of these problems. We can avoid doing these redundant activities. We can. So let me say that for the next slide. Just what I want to mention here is that one of the great ways that we can achieve this is using virtualization. So in this case, virtualization potentially adds security benefits over a traditional environment. So I think it's more than just simply saving costs or saving electricity or those kind of things. I mean, there are actual security benefits which we can add that you cannot do without virtualization. And I will talk about that in more detail. But basically, for these problems I just mentioned, I want to kind of show how we can solve these problems using virtualization. So for example, the things like the software updates or scanning for a virus, why do we need to do that inside each virtual machine? Couldn't we potentially do that from outside the virtual machine? Maybe because either we do it from the hypervisor or from another security VM, which has access to the memory of the guest or has access to the storage of the machine we want to protect. Right, so now, if we can do it this way, we get a lot of benefits. One simple one is that the whole design is going to be simplified because we don't need to be installing agents in all of the machines. We potentially just need to keep the agents located in one central location. This could be a central repository, this could be the hypervisor, this could be a security VM. But in general, you keep all of these in one place, which when you want to now do some task on a given virtual machine, you just take it from this central location and deploy it into each virtual machine. So another benefit to this is take scanning for a virus, for example. We don't need to do the scanning inside each virtual machine. We could potentially do the scanning from a central location which has access to the hard disks of each of these virtual machines. So now we get the benefit that we would only scan a file once globally rather than potentially scanning it on every virtual machine. Now, another big benefit to this is that if you consider the case that I mentioned earlier as far as the security risk, so if you have malware on the workstation, it can disable your agents. Right? So now what if we can kind of achieve the same goal but without having the software inside the virtual machine? So in that case, even if the machine gets infected, there's no security software there to disable. The security software would exist outside of the virtual machine. Okay, so now taking the example I gave earlier of kind of the enterprise environment, this is more what it would look like if we were talking about a virtualized environment and we were using something like this prototype to protect it. So now these workstations would be replaced with virtual machines. We don't specifically have to be talking about just for employee workstations and using thin clients and things like that. I'm just using this as an illustration. These could obviously also be servers like web servers or database server, things like this. So in general, when we talk about a workstation now, we're replacing it with a virtual machine instead of, for example, a laptop or a desktop. And when we talk about a domain, now rather than talking about something like the Active Directory, domain server, now we're talking about like the hypervisor, which is controlling all of these virtual machines. And now these agents can exist in one central location rather than be located in every virtual machine. Okay, so now the benefit that we get to this approach, now I should take a step back and just mention there are some cases where you need to do something inside the virtual machine, maybe because it's technically challenging to do it from outside of a virtual machine. For example, from outside the virtual machine, we might have access to the guest physical memory or the guest registers. Like that might be all we have. So we can inspect the memory of the guest, but we can't do anything very complicated like read the registry keys, for example. So in order to do that, we occasionally need to do some activity inside the virtual machine. So what this is about is rather than keep these agents permanently inside the virtual machine, just install them when you need them, do the activity, and then remove them again. So that an agent only exists inside the virtual machine for a very short period of time, long enough to achieve its objective, and then it's removed again. Right, so if you think of the movie Matrix, it's kind of similar to this, where you've got these agents which can kind of pop into this virtual world at some point and can then leave again. It's somewhat of a similar analogy. And this whole task is very fast. So this is on the order of, let's say, 20 or 30 milliseconds to do this whole thing. So, I mean, even if there is something inside the virtual machine that's looking for the agent, it has a very small window to detect the agent. And we do various tricks to make this window even smaller, which I'll explain in the second half. Okay, so in a nutshell, this is kind of how it works. We can inject an agent into the virtual machine without the help of the operating system. Now, the reason that this is important is that the operating system might actually be compromised, so we might not be able to use the OS native facilities to do it. And another point is, let's say that we want to load a driver inside the guest to do some task. So the standard way to do that would be to use some API, like CW load driver, which requires, for example, a registry path. So this means we need some persistence inside the virtual machine. We would need to have a file inside the virtual machine for the driver, and we would need to have something in the registry to reference the driver. Now, this obviously would be a weakness because if there was a rootkit, for example, inside the virtual machine, they could detect the presence of this driver and actually disable it. Or they could hook the API to load drivers, and they could simply interfere with the ability to load a driver. Right? So in general, we don't want to rely on the OS in order to achieve this because that makes it kind of a weak point for malware to disable the agent. And as far as how it works, we basically inject the driver ourselves into the virtual machine. We do the relocation ourselves. We load the driver ourselves. We don't use any of the OS driver loading facilities. And it's not custom code. You don't need to write shell code or anything like that. It's basically just a standard Windows driver. You compile it using the Microsoft DDK and so on. So it's basically just a standard driver which you can inject into the virtual machine in order to do some activity. And of course, it has access to all of the same APIs that a typical driver would. So since I'm talking about being able to inject agents into a virtual machine, it might cause one to wonder, what about VMware tools? Don't they already give you a way to inject an executable into a virtual machine? So the big difference is that this isn't really designed for security. This is just kind of something for doing some simple administrative tasks, but it's not really, it won't work in this case that I'm talking about where you have something malicious or hostile inside the virtual machine trying to prevent it. So according to my understanding of how VMware Tools does this, they basically put the executable you want to run onto an ISO, and they load the ISO inside the guest virtual machine. So, for example, if I'm a rootkit and I want to prevent this, I could just simply hook, GW create process, or hook the APIs involved with creating a process. And if the process is being launched from a CD, I just return an error. So it's just pretty trivial to disable this kind of thing. Right? So in general, VMware Tools works fine. It just doesn't, it's kind of a different use case than what I'm talking about. Okay, so our prototype was designed on, as far as the test environment we used a VMware ESX server, and we've used a security API which is provided by VMware called VMSafe. For someone not familiar with VMSafe, it's basically like an API that will allow you from a security virtual machine to monitor or inspect or interact with the other virtual machines. So in general, this gives you a way to read or write the physical memory of another virtual machine, to read or write its registers, to modify the registers, some general activities like this, and also gives you a way to, for example, effectively put breakpoints in another virtual machine. So also this API was written by a good friend of mine, Oded Horowitz, who I believe is here. So if there are more questions on it, I think they might be more suitable to him. But in any case, he also has a security background, so it was kind of designed with security in mind. So I would encourage you to take a look at it sometime. Now, our interaction with VMSafe is primarily in terms of being able to read and write to the guest physical memory. So using the VMSafe API, we can basically put breakpoints inside the guest virtual machine, which will enable us to take control of the virtual machine, and then we can inject our code into the virtual machine. I'm going to explain in more detail how that works. The only thing I want to mention is that these APIs cannot be used by any virtual machine. In case you're wondering, if I'm able to use this in order to inject code into another virtual machine, why can't a malware do it? And the basic idea is that these APIs can only be used from the security VM, and this VM should only be used for this purpose. You wouldn't be running network services or other things that would make the machine vulnerable. So the prototype basically looks like this. Basically, this virtual appliance VM or security VM is where our software is running. So it's basically just a user mode program. It doesn't need to do anything in the kernel or do anything fancy. This is just a standard Linux, standard Linux OS, and our program is a standard Linux program. And we use a VMSafe to communicate with the VMware hypervisor, and basically, whenever one of these user VMs, which we are protecting, is going to be loaded, we will get an event from the hypervisor. So we basically register ourselves with the hypervisor, and then we have a channel of communication with the hypervisor. Whenever various events happen in the hypervisor will inform us and give us a chance to do something before the event happens. Okay, so now for the rest of this talk, I'm going to talk about a particular scenario to kind of help you to kind of envision how this would work. So for this prototype, I'm going to use this to do antivirus scanning from outside of the user VM. So now this is just one example. We could obviously do a lot of other things, but just for the purpose of illustration, I'm going to take our antivirus software, take our antivirus signature sets, and I'm going to put these on the security VM, and I'm now going to scan the user VM, and I'm going to run a virus inside the user VM, which will be detected by the security VM. So, the general idea here is that when we detect this virus, it means it's already on the machine and it's about to run, because we're doing memory scanning here rather than file scanning. So this basically means that when we get an event, when we detect a virus, this machine would have been infected if we were not there, because the user has somehow caused this program to run. So if there was no security software here, the machine would be infected already. If there was a kind of a traditional AV, we might have detected it as soon as the file was placed on the machine. But in this case, because we don't have direct access to the file system of the virtual machine, we're doing memory scanning. So we're basically taking our antivirus signature set and checking the memory pages as they're executing. Okay, so now I'm going to talk about basically how it actually works in more detail. The only thing I want to mention from this slide is that when we inject, the reason that I talked about a driver previously is that we want our agents to run in kernel mode simply because there might be a rootkit inside the virtual machine. So for example, if we inject an executable program like a .exe, it's going to run at user mode. So if there was malware on the machine, if there was a kernel rootkit, it could disable our agent because we're running at a lower privilege than the rootkit. So at least we always need to be doing our activities at ring 0 so that we have the highest privilege possible, so that we can do things like disable interrupts if we need to, and those kind of things. So we want to be sure that we have enough privilege to basically prevent some rootkit or some other hostile code inside the machine from interfering with the agent. Okay. So let me first mention about the memory scanning as far as how it works, since it might seem that this would have a high performance penalty, but when you kind of see how it works, I think it would be more clear why it doesn't. So in general, VMsafe gives us a way to put breakpoints on page execution, so that whenever a page is about to execute, but before it executes, we have a chance to inspect that page and take some action. So we basically start by putting a memory breakpoint on, in effect, all physical pages, so that whenever any page in memory is about to execute, we get that event from the hypervisor and we have a chance to scan that page for malware. Okay, so if the page is clean, we can simply remove that execution trigger. So we do not need to scan the same page twice. So we scan it once, we remove the trigger. Whenever that page runs in the future, we will not scan it. So it's kind of a one-time hit. Now, we do need to add a write trigger, though, so that if the page later changes, then we basically need to scan it again. So in general, if the page doesn't change, we never scan it again. If it changes, we will get that write breakpoint or that write trigger, and then we will re-enable the execution trigger. So if a write event happens on the page, we don't scan, we simply re-add the execution trigger, so that after all of the writes finish and it tries to execute that page, we will then scan it again. Okay, so that's the first step, is just to do the memory scanning and find the threat. So the next step is we need to prepare the agent which we want to put into the virtual machine in order to clean up the threat. So obviously we need to read in our agent from disk. Now this doesn't exist inside the user VM, this exists on the security VM. So within the user VM, our agent will never exist on disk. Our agent is completely, it's completely non-persistent. We don't have any file inside the user VM. We don't have any registry keys. It only exists in memory while it's running, and it's removed when it's no longer running. So the actual loading of this primarily happens on the security VM. Now, the problem is that our Linux VM, our security VM is a Linux OS, so we need to basically parse the PE format ourselves to, in order to load the agent. The main task here is just to simply find out, like, we don't do anything too complicated. We mainly just need to find out how big is this, how big is the agent, like how much memory will it take up, and find out what APIs it's using. Because, for example, if the agent is using the debug print API, we need to link that import with the address inside the user VM, right? So obviously, the address of the kernel in each user VM may be different. So whenever we want to inject an agent inside a particular VM, we need to line up the imports of the agent and the exports of the kernel from the user VM. So we need to link them so that our agent knows the correct addresses of the APIs. One other step that we need to do here is that we need to find where the kernel is located inside the user VM, because it's not always located at the same address, and we need to find the export table so that we can find out the address of those APIs. Right? So now we've got our agent loaded inside our security VM. Now we want to put it inside the user VM. So we need to find somewhere inside the user VM to put it, because all of the memory inside the user VM belongs to the user VM. In the original story, we have our own agent inside the user VM. It's manually installed inside the user VM, so we own a portion of the user VM. We can start it like a regular process, so we have our own memory, and we have a file on disk, and so on. But in this case, we don't own anything inside the user VM because we're basically deploying it on the fly. So even just finding somewhere in memory to put our agent is a challenge. So now the technique that we came up with to do this is to, now in Linux you have kmalloc as the way to allocate kernel mode memory. In Windows you have exallocate pool as the way to allocate kernel memory. So one good way to find memory which is available inside the user VM, which is allocated, meaning it has a virtual address, because in general we're dealing with physical addresses, so we need some way to find some actual allocated and committed memory inside the kernel. And we basically need to find memory which is unused, because if we just simply pick a random page and put our agent there, it may be overriding some data which was being used by the user VM that it thought was available. So, for example, we cannot just simply take some unused page, because what if the kernel itself decides to later use that page? So we need, in general, we need some way to find memory which we can control and which will not be used. So a good trick that we found to do this is to put an execution trigger on exallocate pool itself, so that after the memory has been allocated, but before the memory has been returned to the code which requested the memory, at that point, you have memory which has been allocated but is not yet used. So by basically, in effect, putting a breakpoint on the return instruction of exallocate pool, we have memory which is allocated but unused. And so we temporarily hijack that in order to bootstrap our agent. So it looks something like this. Some code inside the guest VM, most likely the kernel itself, because this happens very early in the boot process. So most likely the code who's calling exallocate pool is some kernel code itself, something inside NTOS kernel. So now this is going to call exallocate pool. We will then get a breakpoint. We will inspect for example, the parameters to see if it meets our criteria. So for example, is the memory big enough to fit our bootstrap code? Is it non-pageable? I mean, it doesn't have to be non-pageable, but there's, let's be safe and get memory which will always remain in, pick a page which will always remain in memory, won't be paged out. Okay, and then we're going to temporarily hijack this memory, meaning that we are going to put the code inside this page. Now, this might not have originally been intended to store code, but all of the kernel mode pages are executable on Windows. That there's no DEP in the kernel, at least for any version that I've looked at. I didn't look at Windows 7 yet. Okay, so now we put our own bootstrap code there. Now, all that our bootstrap code does is just allocate more memory. So right now we've hijacked some temporary memory which will belong to something inside the user VM, and we just hijack this to allocate more memory. Now the memory that we allocate will be permanent and will belong to us. So our bootstrap code simply allocates enough memory to fit our agent in the future. So now we've got this permanent memory available for our agent, but we don't actually put the agent there. We just allocate the memory for it, so that when we need it later, it's there. But now, the important point here is that if there was, for example, a rootkit trying to detect the presence of our prototype, they wouldn't see anything unusual. This would just look like another allocation from the kernel. And another point is that this happens very, very early in the boot process, before even any boot drivers have been loaded. So in general, unless the rootkit has really, for example, directly modified the NTOS kernel binary, or it's done something at a very low level, in general, this code is operating even before the rootkit would have a chance to load. Okay, so now at this point, we've got the memory inside the user VM, and now we need to cause it to execute. So in general, there's kind of two situations we're dealing with here. One is that the code which we have interrupted was running at ring 0. In other words, our antivirus signature has detected malware inside the kernel. So in general, our antivirus signatures are scanning the memory pages. They don't care, it wouldn't matter if that page was a user mode page or a kernel mode page. It just matters that it matches some antivirus signature. So we may have the malware which is running at ring 0, or we may have the malware which is running at ring 3. Now, obviously, in most cases, this is going to be ring 3 because most malware is user mode programs. Okay, so now, if this is running at ring 0, we have a simple task. We can simply change EIP to point to our agent's memory if we're already in ring 0. But in most cases, we're in ring 3, and we want to synchronously call our agent. So synchronous is the keyword here because we want to, we are detecting the malware just before it runs. So at this point, it hasn't had a chance to do something malicious, but if we let it to continue running, it want some kind of delayed event where we later react to the malware. We want to kind of synchronously interrupt the malware flow and go directly to the agent before any of those instructions have a chance to run. So the way we will do that is by forcing a CPU fault, which we specially catch. Okay, so the idea is like this. We know the EIP. We know the EIP of the malware page, right? So we have a memory page which we detected malware on, and we know the EIP because we have all of the guest registers available to us. So we can read the guest registers or we can modify the guest registers. And EIP is just another register. So we basically look at where is EIP on this page, and we will now insert an invalid instruction at that location, so that whenever the guest VM resumes, it will immediately trigger an invalid opcode fault. Now, there's no reason it has to be an invalid opcode. It could be any kind of fault. The point is that by triggering a fault, we make a transition from ring 3 to ring 0. So in general, when you have some kind of CPU level fault, this will go to some entry in the IDT. The IDT is the interrupt descriptor table, and it's basically a list of all of the exception handlers. So the other reason that I chose the invalid opcode is that it's a relatively infrequent fault. So it's not very likely that in this precise moment we will, by coincidence, have another fault. This is why, for example, we wouldn't want to use a breakpoint handler, because if we are going to hook the int3 handler or the debug breakpoint handler, and then just by coincidence another program were to do an int3, that would cause our agent to be invoked. So here our goal is to get our agent invoked using some fault which is relatively infrequent. But we could, of course, also just use a custom interrupt which is unused. So I just want to be clear, it doesn't really matter what kind of fault we use. So once we trigger this fault, the CPU will go to call the fault handler. Now, when we go to call the fault handler, it won't ever actually be called. So we are not disturbing the normal flow of the user mode VM, because we are going to put a page execution trigger on the interrupt handler. So in other words, for this invalid opcode fault handler, we have a page execution trigger. So that once this invalid opcode occurs, the CPU tries to call it, and at that point, the VMware hypervisor detects this event and passes it to us. So when I say we put a breakpoint, I don't mean a physical breakpoint inside the guest. There is no sign inside the guest that we have a page execution breakpoint on the invalid opcode fault handler. So in that sense, it's a virtual breakpoint. Even if there was a rootkit that knew that we used this technique and they were, for example, checking the invalid opcode, fault handler entry inside the IDT, they would just see the original invalid opcode fault handler entry. We don't change anything inside the guest virtual machine. So once the fault handler executes, we get the event notification from the hypervisor, and now we can just manually change EIP to point directly to our agent. Now, another benefit to that is that if we want, we can also guarantee that our code won't be interrupted, because our agent is being called from an interrupt handler, and while the interrupt is being handled, that CPU will not run any other code. So we basically have full control over the CPU. Okay, so this is just to kind of visually demonstrate what I was talking about. Now, we're first going to replace the malware page with the invalid opcode. In this case, for example, you can use the UD2 instruction. It's an Intel-defined. It is an actual opcode which is guaranteed to generate an invalid opcode. So it's basically an opcode that it's like the F00F, if you remember kind of the Linux foof thing. It's basically like this. So in general, we use an instruction which we're sure is going to cause a fault. This will cause the invalid opcode fault handler. This invalid, when this fault handler is called, this is going to cause our agent, or rather, this is going to cause our prototype to be called in the security VM because the hypervisor is informing us of the event. And now we are going to change EIP to execute our agent. So again, where this agent code is running is now in that memory which was previously. Okay, so I want to try to demonstrate this again. Like this agent code, it's putting it in that permanent memory which we allocated for the agent, but only at this moment do we actually put the agent code inside the virtual machine. So up until this point, there has been no actual code of our agent inside the virtual machine. We inject it right at the time before we call it. Now, when this is called, if we want, we can control how we do this. But for example, you can call this directly from the default handler so that this agent is will directly execute as an interrupt handler, meaning that it has monopoly over the CPU until it returns from the interrupt. So in general here, this is just illustrating that we're changing EIP to point to our injected agent. Okay, and then after our injected agent finishes, it's going to return back to our prototype. Now, how does that happen? Basically, when we invoke the agent, we're invoking a function inside the agent. So when that function returns, we know that the agent has finished. We can do that by simply putting a page execution trigger on the return address of that function, so that once that function returns, we get another page execution event. Another way that we could do that is by having a special page that, for example, we put a page write trigger on that page, and our agent can write to that page when it's finished, basically to trigger a VM exit. In this case, though, I tried to design this so that the agents don't really need to know or care how they're loaded. So the agent code itself doesn't do anything special. So I don't know if this is too small to see, but basically here's a very simple agent. Basically, we just export some function from our agent. Here it's called inGuest function. So we check the export table of the agent to find this function, and we simply invoke this function. That's all we do, right? So you can see that all this code is doing is calling debug print to print a message, and then it's going to terminate the process. So you can see this is a fairly simple piece of code. Now, the reason this works is because we've done this synchronously. So this code is executing in the context of the process which triggered the malware event, or that we detected. So we can simply terminate the current process as a way to remediate the malware. Okay, and now once the agent returns, we simply remove the agent again. Meaning we'll keep the memory there, but we'll restore it back to its original value. So except for that very short time where the agent is executing, it will, this memory will basically be allocated but unused. We temporarily execute the code. Once it finishes, we remove it again. Now, this could entirely happen from an interrupt handler, so that during the time the agent was executing, no other code could be running under that CPU. So, in general, we're trying to make a very small window where something inside the user VM could detect or disable the agent. Okay, so that is basically what I wanted to talk about. I want to do a demo, but I'm not yet sure. I'm not yet sure about the network. When I was trying to connect earlier, I couldn't get any connection here. In general, what the prototype is doing is I picked a particular virus. So this is just using w32.gamima, so this was the virus that I believe was found on the International Space Station. So there's no particular reason we chose this virus. Just simply, it's one that can be detected. And then our agent is injected to simply terminate the process. In case I cannot get the demo to work here, someone can see me after, and at least it works from my hotel room. So I don't know about the network here, but in any case, someone can find me if they're interested. Let me just briefly mention about the performance here. So in general, these are absolute numbers. They're not really meant to It's just meant to give you kind of a rough ballpark for how long this thing takes. It's not a very scientific benchmark. So all I can say is that basically for this whole process to run, it usually just takes about 20 or 30 milliseconds. So the startup time, the slowest part is actually finding where the N2S kernel is inside of the user virtual machine. So we don't know where it is. We need to basically do some kind of trick or some kind of scanning to find it. And then we need to install the bootstrap code. We need to load our agent and apply the relocations to basically match the user VM we're going to inject it into. So that's a one-time cost. We do that just once. Basically, whenever a VM first boots, whenever it first starts to boot, we get an event from VMsafe to inform us that a VM is starting. And at that point, we do these startup steps. Now, the important one is this inject and execute agent driver, because this is the one that happens repeatedly. So we try to make sure that this part is fast, because every time we detect a malware event, we need to do these steps. So in general, this is pretty quick. It just takes a few milliseconds. And if we terminate the process, we don't need to do anything further, because the agent will never return. Now, if we want an agent which will actually do something like clean up the process, but then will otherwise continue. So for example, if we're trying to clean up a virus which has infected Microsoft Office, we might want to simply clean it, but otherwise allow the program to run, because otherwise, Microsoft Office won't, Microsoft Word, let's say, it won't run because we terminate the process once we detect some malware. So in this scenario, we want to clean up the virus, but we want to let the program run. So in that case, we now need to kind of restore the original state after our program finishes to run. That basically means removing the agent, and we're now in kernel mode. We need to go back to user mode where that malware page was that we originally interrupted. So that's what I mean by restore the original state. So the total time in general here you can see is less than 10 milliseconds. So if there is something inside the user VM which was attempting to detect this, they've got a fairly small window to do the scanning. And another point to make here is that we don't rely on any APIs. When I say the prototype itself does not rely on any APIs other than EXAllocate pool. That is the only API that we use, and that happens very early in the boot process, probably before any rootkit is actually loaded. So an agent which we're going to inject might be detected, because, for example, here the agent which I've demonstrated, this agent will terminate a process. So, for example, a rootkit could potentially hook into terminate process to detect that particular agent. So if a rootkit knows what an agent does, it can potentially hook something that the agent will call, but that would be an attack against that particular agent. Right? So the idea here is to make a framework which can be used to load an arbitrary number of agents. So we might even inject a different agent depending on the virus that's detected. Maybe for one virus, we simply want to terminate the process. For another virus, we might want to do something more complicated. So we can decide which agent to inject after we detect the malware. So in general, we have some flexibility here. Like if, for example, this was for updates instead of, for the security side, we could, for example, inject we detect the antivirus. Let's take a different example. Let's say we detect some Windows component is out of date, so we want to trigger a Windows update. So we might inject some agent inside the guest to trigger an update. So it doesn't have to just be for this kind of antivirus thing. Just the point is, we've tried to make a way to inject an arbitrary agent or to deploy an arbitrary agent inside of the user VM, run some task, and then remove it. Right? So in general, this code can work on any legacy Windows driver. There's no reason this has to be Windows, but given that most of our customers are using Windows, it's reasonable here that we focused originally on making this work for Windows, but this could also work on Linux. In general, this can work on any kind of legacy driver in that you just compile this using the DDK. The only thing is that we don't use the driver entry because that expects a registry path as a parameter, and we're not persistent. We don't have any registry keys or any files. So the only difference is that we provide a custom function which you call. So if you simply move the code that you want to run in your driver into this function, that's all you need to get this to work with the legacy driver. In general, this can handle a hostile environment, meaning even if it's infected with a rootkit, the chance for the rootkit to interfere with the agent or with our code executing is very small. It's a small window. that there might be some possibilities to detect a particular agent, but I don't believe there's a generic way to detect this or to disable it. Let me say that differently. I think that you could potentially detect it even by just using something like timing to just see that, okay, things are running slower than you expect, but you can't do anything about it. That might be a better way to explain it. So the only thing that they could do is say, okay, we know that there's something strange here, things are taking longer than expected, so I won't run my malicious code, which would be fine with us, right? So in general, I think that they might be able to see that there's some kind of virtual environment. They might be able to even detect some characteristic of our, of our prototype, but I don't think that they can actually do something to prevent it from working. And of course, I don't want to say that we've entirely eliminated malware threats, because as I've mentioned, they can disable a particular agent. So I just want to say that we've certainly raised the bar, but I mean, I don't think we can fully eliminate, the threat from malware. Right. Now, I've talked here about this, this antivirus scanner, but like this was just a proof of concept to kind of demonstrate, the prototype, right? So, in other words, the antivirus scanning was not the important part. That was just a demonstration. So there are various problems with doing antivirus checking with a memory scanner. There are some various problems with that. So this is just kind of meant to demonstrate the idea. But the bigger idea is to use this platform as a way to kind of build deployable agents to do some arbitrary task which you can inject inside a virtual machine, and it doesn't really matter too much what the agent does. So kind of where I'd like to go from here is either to build other examples beyond just the antivirus scanner that can use this prototype, or to take this prototype onto other hypervisors. So if anyone's kind of interested in this thing, I would appreciate you to talk to me later to kind of let me know what here seems interesting. If you think that this could be useful for certain kind of agents, let me know. Or if you think it would be more useful for this to be on other hypervisors other than VMware, let me know. I just kind of appreciate to get some feedback from you all. So in general, I think that's everything. I will see if I can get the demo to work, but otherwise, I can show. So in general, I can show you later. Someone can come to see me if you want to see a live demo. Basically, I need to connect to an ESX server to do the demo, and I need a network for that to work. So I don't think that I can get that working right now. So I believe that's everything then. And if you have any questions, please email me.